Hi there. In the previous video, we discussed about the Pythagorean theorem, which is also known as the Pythagoras theorem, and trigonometric functions. By now, you should know that trigonometry is the type of mathematics that deals with the relationships between angles and sides of a triangle. Meaning in trigonometry, we always have a triangle. What is interesting is that from the principles of the Pythagorean theorem and trigonometric functions, we can make new concepts that are very, very useful. For example, the concept we'll be looking at involves the relationship between a side and the angle that is opposite to this side. Obviously, you're used to saying the side opposite to an angle, but it can also be referred to interchangeably. This is Z Online School. In this video, you and I are going to be looking at trigonometry involving the sine rule. We're going to do this in a systematic way, and by the end of this video, you should be able to know what the sine rule is, how to derive the formula for the sine rule, application of the sine rule. At the end of this video, we've got some bonus tips for you, so make sure you watch this video till the end to get the maximum value out of it. Let's begin with knowing what the sine rule is. By definition, it states that in a non-right angled triangle, the ratio of a side and the opposite angle is the same for all three sides. The sine rule will make much more sense if we talk about how it's written. It's sine A over A is equal to sine B over B is equal to sine C over C. Now, what you must note right from the start is we're going to be using the ratios here in pairs. We're not going to use all the three ratios at a time. Usually you'll be given one complete ratio and then one incomplete one, where maybe there's a missing angle that you're supposed to find or a missing length that you're supposed to find. It's rare that you use all these three ratios at the same time. It can be done, but right from the start you might make a lot of mistakes. The sine rule can also be written like this, where we've got the small letters on top and then the signs at the bottom. Now, it's very important to know what these capital letter A, B, and C mean, what these small case letters mean. To get understanding of what they mean, let's talk about a triangle. We know we're using a triangle that is not a right angled triangle, meaning we have no 90 degrees in this triangle. It's either having an obtuse angle or all the sides are just different in length from each other. Let's label this triangle ABC. From what we've learned, you agree with me if you've watched the video about the introduction to trigonometry that the opposite side of this angle here is this one here. Meaning side BC here is the opposite of the angle at A. And simply when you see this capital letter A, wherever you see it in this form or in this form, it just simply means the angle at A. So sine A is sine the angle at A. And just like we did, we're going to label. So if this is the opposite side of angle A, we're going to label it with a small letter A. And we will do the same for B, meaning this side here is going to take the small letter B. We do the same for C, and we have a representation of what we mean. Now, you should note that we're going to be using much of this form of the sine rule. I just prefer to use it because it's got the signs on top and everything, yeah. But everyone has a different preference. The answers won't be different no matter which kind of sine rule you use. Basically, this is the sine rule. Now, how was this rule formed, or how was that formula we're just from looking at sine A over A is equal to sine B over B is equal to sine C over C formed? Well, as you can see on screen, all thanks to the SOHCAHTOA we learned in Introduction to Trigonometry. As you can see, we've got the word sine here, meaning from SOHCAHTOA we'll be using the trigonometric function sine theta is equal to opposite over hypotenuse. As you may already know, we're using a triangle that is not a right angled triangle, and we've labeled it already like that. I'll put the trigonometric function for sine theta here so that you can easily refer to it if you need it as a point of reference. You should understand that when we have a triangle that is not right angled, we cannot use this trigonometric function. Therefore, we form a way in which we can find a right angle triangle in this same triangle we don't have a right angle triangle. We're going to do that by simply drawing an altitude, and by altitude we just simply mean the shortest distance from one of the vertices. Vertices are just like corners, meaning there's a vertex A, B, and C. We draw a line from the vertices, which is the shortest distance to the opposite side of that vertex. So if we come from A here, we draw a line until we reach side A, such that that line we draw and this line BC or side A will be at 90 degrees. That line we draw is an altitude and will enable us to have two right angle triangles. In this question, I'm using an altitude from C because it's easier to imagine as a height. After we draw this imaginary line, we're going to have two right angled triangles. To help you remember that this is a right angle, let me put the symbol there we talked about in the previous videos. And let's label this point of intersection as point O. Remember that we've made a new length here. Let's call that length H because it looks like a height. And basically, since we have a right angle triangle now, we can use this trigonometric function. The way in which we're going to use this trigonometric function is quite different. We're not going to pick any angle we wish. There are specific angles we're going to pick. So to make it easier, I've extracted the two triangles in this triangle. We've got triangle AOC and triangle BOC. Then we're going to do the deriving of the formula here. I'm sure you're comfortable with how these triangles are labeled. You can see that both of them have CO and CO, meaning they both have the same length here, H. It's very important to note that as we are deriving the formula for the sine rule. Okay, now let's finish up some labels. We also have B in this triangle. It's important that we label it. We have A. The first thing before we start using this trigonometric function is selecting the right angle of reference. Whichever altitude you make in this triangle, when selecting your angle of reference, make sure that the height that you make is opposite to the angle that you select as your angle of reference. For example, in this triangle here, we're going to select the angle at A. This will be theta, and therefore H here will be our opposite and the hypotenuse will be B. As you can see, it's the longest side in this right angle triangle. We do the same this side. We take this angle at B as our angle for reference. What you notice in selection is that we make sure that when we are selecting, we don't select anything that we've altered. Not that we don't use the length OA, we don't use the length OB, because this length has been altered. We've cut it into parts that we are not really even certain of. But we can see that there are parts that we haven't touched. For example, this B here, it's the same one here. This A here is the same one here. The H is what we are trying to find, and it's what will enable us to get the sine rule. As you saw in the sine rule, we never had any theta. So this theta here will be replaced by simply the letter of the vertex where we have an angle. And now we can start some replacement here with some substitution of letters. So where we had theta, we're going to put A. Sine A is equal to O over H. Our opposite is H here. And our hypotenuse is B. As you can see, don't really think H always means hypotenuse. It just means a side. Now we make H the subject of the formula. We can do it two ways. You can multiply by B on both sides, and the b you multiply here on the right side will cancel with the 1 in the denominator, and you have your subject. What I'm going to do here is just divide the left side by 1 to make it a fraction so that I have fractions on both sides, and then I cross multiply to get an equation. H is equal to the b here multiplied by the sine A. For now, we are set because we have H represented in form of b sine A. We're going to do this same procedure we did here on this triangle. Sine B is equal to opposite over hypotenuse. Opposite is H and hypotenuse is A, so it will be H over A. And we make H the subject. I'm sure you know my method now. And then cross multiply. We have H is equal to A multiplied by sine B. Everything looks fine. And now what I want you to note is that we have two representations for the same length, which is H. H has been represented as B sine A, and again it has been represented as A sine B, meaning these two are equal. How we show that mathematically is just by this simple statement. Since H is equal to H, B sine A is equal to A sine B. And now we're getting a step closer to how we got the sine rule. What you see here is that our A's and B's here, which are our sides, are like jumbled. We need this A to come over to this side and this B to come over this side. So we need to get rid of the B on our left side and we need to get rid of the A on our right side. What we're going to do is divide by B on both sides for it to be lost on our left side and divide by A on our right side. When we do that, you can see that we'll be dividing by A and B at the same time. So we'll be dividing by AB just like that. That's how we're going to show it. And the B and the B cancels, the A and the A cancels. And now you can see that we have our sine rule. Sine A over A is equal to sine B over B. Very interesting, as you can see. But if you can remember, we had another representation of the sine rule. That is also gotten by just changing what we're dividing by. If we divide by sine A sine B, then we're getting rid of the sine A on our left side and the sine B on our right side. Therefore, we'll be left with, if we cancel the sine A and the sine A here, the sine B and the sine B, we'll be left with B over sine B is equal to A over sine A. As you can see, the order is a bit different, but these two things are equal. So if I was to bring the A over to this side and the B this side, it won't change anything. This is how basically we get the sine rule. One question you might have is, how is the third ratio sine C over C gotten, or C over sine C gotten? Well, it's basically the same principle. Like you heard me earlier, we can change the altitude that we use to derive this sine rule. And now, when we do that, we get a pair of different ratios. Here we use this altitude because it's much easier to understand if we put it as our height than if we draw one from A to this A. If we use this altitude to make another set of ratios that are equal to each other, you can see that we will have C's and B's. Therefore, after we do all our math exactly like this here, we are going to get a result of, let's say, sine C over C is equal to sine B over B. And for the other one here, obviously we can have B over sine B is equal to C over sine C. Then now, since two of these will be equal to each other and another two will be equal to each other, that one which is equal to either of these will make it possible for us to equate all the three ratios to each other. It's like if this one is equal to this one and then this B is equal to this C, we can confidently say that all these three are equal to each other. That's how we derive the sine rule. it should be noted that we can use another altitude from B to this other side AC, and what will happen is just that we'll have a different set of letters. We might have AC, and basically it's the same principle as I was saying. The A will be equal to the B, and if the A is again equal to the C,